Hello class, welcome to this lesson on Introduction to Hypothesis Testing. So what we want to do is we want to basically discuss, the application of hypothesis testing, like what is the procedure. What we want to do is introduce the notion that when we do an experiment and we want to test a claim about a population, we want to be able to do hypothesis testing. So we want to be able to set up our null and alternative hypothesis just like you would in a science experiment. So we're going to take you through this process. So the goal is to be able to state the null and alternative hypotheses and understand the hypothesis testing procedure and how to do a few things in that procedure. Okay. So it's just a basic introduction, and we're going to be introducing a lot of vocab in this lesson. So let's discuss statistical hypothesis testing. So this is a process that you use to evaluate claims about a population. So if you want to study the average age of the United States citizens, then your parameter is the average, right, that you want to evaluate. Okay, so in this case we want to evaluate claims about a given population, whatever population you're studying. And in the example that I gave, it would be United States citizens, right? So it's a decision-making process used for this purpose. In this process, you must define the population under study, aka in our example, United States population. State the hypotheses that will be investigated. In our case, we want to test the mean, right? We want to test that the mean is, let's say, 80 years old or whatever. Let's say that the average age of the United States citizens is 60-something years old. Then we want to test that. Give the significance level. We'll talk about what the significance level is. This is just a hypothesis process. Select a sample from the population. This is the sampling techniques that we talked about, the sampling, random sampling, stratified sampling, cluster sampling, systematic sampling. This is the ones that we talked about in the other lesson in class, okay? Then we want to collect the data and then do some calculations that are required for the test in order to reach a conclusion. Okay, so in our case, what's the average age equal to, 60-something? Does it dramatically differ from that? There are three methods used to use hypothesis testing. We're going to be looking at the traditional method in this lesson. And the other lessons, they'll be kind of interspersed in other lessons in this chapter. Okay, so we will discuss the traditional method, as we said. A statistical hypothesis is a conjecture about a population parameter. It's all about the parameter. Remember, the purpose of statistics of this branch of statistics is to basically study the parameter, study the population. How do we study the population? We take a sample and we calculate a statistic. That's what it's called. When you calculate this from a sample, it's called a statistic. When you calculate from a population, it's a parameter. So some examples of parameter are the average, the population mean, population standard deviation, population variance, and the other one that we mentioned was population proportion. So those are the things that we want to study depending on, the context. And then this conjecture that we claim about may or may not be true. That's what we want to test. So there are two types of these hypotheses that we set up. There's the null hypothesis and the alternative hypothesis. So let's discuss the null hypothesis. The null hypothesis, the symbol for that is H sub 0, and it's a type of hypothesis that states that there is absolutely no difference between the parameter that you're trying to study and a particular value. So there's no difference at all between your observed value and the parameter value. So basically they're saying that it's a statement of equality. So if there's no difference, that means that they're equal. So this is a statement of equality. The alternative hypothesis, symbols for that are H1 or HA, is a statistical hypothesis that states that there is a difference between the parameter and your observed value. Okay, so there is the existence of a difference. So if H0 is a statement of equality, HA is a statement of inequality. The alternative hypothesis is also known as the research hypothesis because this is the hypothesis that you're interested in studying. Okay, so we're going to look at a situation now so that you can see what we mean by that. So situation A, a medical researcher is interested in finding out whether a new medication will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of the patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged after medication? The researcher knows that the pulse rate is 82 beats per minute. So what we're saying is that the claim is that without the medication, the pulse rate is 82. So no medication, average pulse rate, we'll say average, is 82. Okay? Is means equal, right? So if a thing is, that really just saying equal. So that's the claim. But we know that the hypothesis for the statement of equality belongs to the null hypothesis. This is a statement of equality, right? So therefore, that belongs to the null hypothesis. So mu is equal to 82. All right? So you start with the claim, and then you assign which one it belongs to, depending on if it's equal or not. All right? And then in this case, you're interested in finding out whether the medication will increase or decrease the pulse rate. So this means that you're saying it does not equal to 82 because that's what you want to test. Okay, you want to see if it increases or decreases. This is a two-tailed test because there is no direction. It could either increase or decrease. All right? For situation B, a chemist invents an additive to increase the life of a battery. If the mean lifetime of the battery without the additive is 36 months, then what are your hypothesis statements? So it says here that the mean lifetime of the battery without the additive is 36 months. So that's our claim, is that the average lifetime without the additive is 36 months. So that's our claim, and now also that's a statement of equality. So that belongs here. So mu is 36. Now the claim doesn't always belong to the null hypothesis. The idea is to find out what the claim is, and then if it has an equal sign or greater than equal to sign, if it has a statement of equality in it, you assign it to the null. If it doesn't, assign it to the alternative. All right? So now here we're interested in an additive to increase the life of the battery. So that's a greater than symbol. So that means that we're testing that whether the additive increases it or makes it greater. Now this is a right-tailed test because we are doing greater than. So what you do is you want to look at the alternative hypothesis, and that tells you what direction your test is going to take. Okay, look at the alternative hypothesis. So in this case, it was greater than, which looks like an arrow going to the right, so therefore it is right. Okay, so look at that symbol to see if it's going to the right or to the left. All right. So situation C, a contractor wishes to lower heating bills by using a special type of insulation in houses. If the average of the monthly heating bills is $78, her hypotheses about heating costs with the use of insulation are what? So the claim is the average bill without the insulation is 78. So that's average is mu. So mu is 78. Remember the symbol for the population average is mu. All right, and then it says we want to test whether the heat insulation will lower the heating bills. So this is a less than scenario. And since that looks like an arrow pointing to the left, that is a left-tailed test. All right, so here are some of the symbols that we use for hypothesis testing. So we have greater than, less than, equal to, that's not equal to. We also have greater than or equal to, or less than or equal to, which is not here for some reason. But greater than or equal to can be used. So it says if it's greater than, then you use greater than symbol. If it's at least, so sometimes they can say at least, then you would use that symbol. If it says at most, then you can use the less than or equal to. All right, and I also want to be clear about something. So if I give you a problem and I ask you to find the alternative or the null hypothesis. So let's say I gave you that the claim is, so let's say I gave you the claim, right? And I said that the claim is average at least 30. All right, so let's say I gave you that as my claim. Then your claim that is going to be at least is greater than or equal to, right? So greater than or equal to belongs to the null since it has equality, okay? So this is going to be average greater than or equal to 30. And then you swap it to get the alternative. So you do the opposite, okay? So in this example, if I give you the claim, right, then you need, as at that point that you need to see, okay, well, this is greater than or equal to, so then this has to be less than. So if I directly give it to you, then you can go ahead and assign this. Otherwise, look at the problem. Okay, so the null hypothesis contains the equal sign. So some kind of equal sign. So it could be greater than or equal to symbol. It could be less than or equal to, or it could just be the regular equal to. For the right-tailed test, the inequality for the HA points to the right. For the left-tailed test, the inequality for the HA points to the left. So for right-tailed test, it points to the right. For the left-tailed test, it points to the left. And this is called the directionality. So to determine the directionality in general, you look at the alternative hypothesis, or HA. A claim can be stated as either the null or the alternative. In our examples, it was generally the null, but that's not always going to be the case. So sometimes you'll end up having a claim or a statement that is assigned to the alternative. So let's look at this example here. So we have, for part A, a researcher thinks that if expectant mothers use vitamin pills, the birth weight of the babies will increase. The average birth weight of the population is 8.6. So here, the claim. So right here, let's just go ahead and underline that. That's our claim right there. The claim is that the average is 8.6. Okay. So where does that belong to? Well, that belongs to the null because it's is means equal to. All right. So H0, and it says average. The symbol for average is mu. Okay. So we have here mu is equal to 8.6. And then for our HA, what are we trying to study here? So is this not going to be equal to, or is it going to be greater than or less than? Well, it says that if expectant mothers use vitamin pills, the birth weight is expected to increase. So we want to test that. So therefore, mu is greater than 8.6. All right, so for part B, let's go ahead and underline our claim. An engineer hypothesis that the mean number can be decreased in a manufacturing process of USB drives by using robots instead of humans for certain tasks. The mean number of defective drives per 1,000 is 18. So this is, we know that that's our claim, and we want our research hypothesis or alternative hypothesis is that we want to test that the mean number of defects can be decreased by using robots. Okay, so in this case, this is, since it says is 18, it means equal to 18, that's null. Okay, so, and it says the mean is mu. In our HA, we want to test whether it decreases, can be decreased, so that's the less than symbol, so mu is less than 18. A psychologist feels that playing soft music during a test will change the result of the test. But the psychologist is not sure whether the grades will negatively impact or positively impact. So the psychologist doesn't know whether the grades will be higher or lower. In the past, the mean of the scores was 73. So that's our baseline that we want to test, okay? So we're saying for the null hypothesis, there is not going to be any difference whether we do music or not. So they're saying that it was, that means it was equal to 73. So that's the null, equal to. And then the HA, we're saying we're not sure whether it's greater than or less than, so that means we're going to say it does not equal to 73. So it could be either greater than or it could be less than, but we're just saying it does not equal to. Okay, so in this example, this is a two-tailed test. Example A, this is a right-tailed test because of the greater than symbol, so that's a right-tailed test. And this one, because it's less than, is left-tailed. Alright, so let's look at a statistical test. So a statistical test uses data obtained from a sample. So what you got to do is, if you want to test a population parameter, you got to get a sample, right? You got to get a small sample from the population. So you're going to use the data from that sample, make a calculation, and then use that calculation to make a decision about whether you should reject or fail to reject. Okay, so to make a decision about whether the null hypothesis should be rejected or not. Should be rejected or not. So you're either going to fail to reject or reject it. So the test value or test statistic is the numerical value obtained from a sample. Oh, I'm sorry. So the test value or test statistic is, I said sample, right? This should say statistical test. Statistical test. Okay, so the test value or test statistic is the numerical value obtained from a statistical test, which in turn is obtained from a sample. Okay, so just to kind of put those both in there. You can only reject or fail to reject the null hypothesis. Okay, so we generally never say accept. Okay, and the reason is because you can never really prove that it's the parameter is equal to the null hypothesis. Okay, so you can only say whether you had enough evidence to reject it or you did not have enough evidence to reject it. Okay, so that's generally how it works when you're doing statistical testing. There are 4 possible outcomes. All right, so we can reject the null hypothesis when it is true, or when it is actually true. So we don't know whether it's actually true, but like if it is actually true and we rejected it, then this is a type 1 error. Remember, let me be clear. The only way we know that it is whether something is actually true is if we sample the entire population. But there's no way that we're going to sample every single person in the population unless you had enough time, money, etc., resources. So this is why we are doing this based off of probability. So here, there's a probability that our hypothesis or our decision was incorrect. Okay, so this is the type 1 error. So we reject the null hypothesis when it is actually true. We reject the null hypothesis when it is false. That's correct. If we fail to reject the null hypothesis when it is true, that's also correct. We made a correct conclusion. If we fail to reject the null hypothesis when it is false, then we call this a type 2 error. Okay, so when it is false, but we fail to reject it. So think of it in terms of a jury trial. So in a jury trial, our null hypothesis is, well, the person is innocent, right? So the person that is under trial is innocent until proven guilty. So the H0 assumes the person's innocent. Our alternative is the person is not innocent, okay? Or in other words, guilty. So if we reject the null hypothesis, then we're really saying that the person is guilty because we're rejecting the fact that they're innocent, right? So that means that we're saying they're guilty. But if they're innocent, that means we made a type 1 error because we rejected the null when we weren't supposed to. All right, so that's this first box here. If we reject the null and say that we convict them and they're not innocent, then we made the correct decision. So these are correct decisions. If we fail to reject, which means that we don't have enough evidence to show that they're innocent, but they really are innocent, then we're doing things correctly. We made a correct conclusion. If we don't have enough evidence to reject the null, then we don't have enough evidence to say whether they're innocent or not, right? So since we're not rejecting it, we're not really saying we're saying that they're not innocent, or we're failing to say that they are innocent, right? So in other words, we're saying that they're not innocent. In that case, if they're not innocent, or I'm sorry, we're failing to say that they're innocent, okay? So we're failing to reject this, okay? So we don't have enough evidence to show that they're innocent, but they're really not innocent, so that would be an error, okay? So they're actually not innocent, but we fail to do that conclusion. So these are the two problematic ones. So in the first case, we're rejecting the null hypothesis when we weren't supposed to. In the second case, we're failing to reject when we were supposed to. We were supposed to reject it because the person is not innocent, okay? Okay, so like we said earlier, the only way to prove something statistically is to use the entire population, right? That's the only way. That's why we have these errors, right? Like, why can't we show that it's, why can we have no error, right? Well, the reason why you can't have any error is because you're using a sample. A sample is by definition smaller than a population, right? So if this is your population, then a sample is just part of the population. So of course, if you take a sample, you're really not going to have the whole picture, right? So what we're trying to do in statistics is to get the whole picture from the sample. But by definition, we don't have the whole picture. So therefore, we're gonna make an error every once in a while, right? So the probability that we make an error depends on how good our sample is, like if we're doing a random sampling, but also it depends on our confidence level and stuff like that. So we'll talk about that in a little bit. So there's always going to be an associated probability. So therefore, the decision is based on probability. So how large of a difference between the observed mean and the claim is necessary to reject a null? So how much is, significantly different? So like if I had mu is 73, and I got a sample, for my sample I got, 80. How significantly different is that? Can I say that they're close enough that I can say that mu equals 73? Or do I have to say that it does not equal to 73 because it's so different, because it's 7 off? Well, we're not sure. This is why we use cutoffs, okay? So this is why we introduce cutoffs to determine, okay, well, that's significantly different or that's not significantly different. So that is where we use the level of significance, okay? That level of significance tells us whether these guys are significantly different. That's why it's called significance. So the level of significance is the maximum probability of committing a type 1 error. The symbol for that is alpha, and the probability of a type 2 error, this is type 2, is symbolized by beta, the Greek letter beta. We're not going to use beta too much. We're going to be focused mostly on alpha. But beta is a thing, and it can be used for type 2 error. All right, so the usual level of significance that we use are 1%, 5%, and 10%. This is similar to the confidence intervals where we use 99% confidence, which means our alpha was 1%, 95%, which means our alpha is 5, and 90%, which means our alpha is 10. So for a significance level of 1%, where alpha is equal to 0.01, there is a 1% chance of rejecting a true null hypothesis. So when you have a significance level of 1%, if you reject the null hypothesis, there is a chance that you're rejecting a null hypothesis that is true, okay? And that is why we call alpha a type 1 error, okay? So then this is a type 1 error. After a significance level is chosen, a critical value is determined, just like in confidence intervals. So this is going back to the confidence interval chapter that we did, so finding the critical value. The critical or rejection region is the range of of possible values, so the range of values here, that indicate that there is a significant difference and that the null hypothesis should be rejected. The non-critical is a range of test values. Sorry, let me write test values here. The non-critical or non-rejection is a range of test values that indicates that the difference was probably due to chance and that the null hypothesis should not be rejected. So basically, if you're in the non-critical region, you're failing to reject the null hypothesis, okay? So that's why it's called non-rejection. You're not rejecting it. The critical region, if you're in the critical or rejection region, you're rejecting the null hypothesis. That's basically what it's saying. So a one-tailed test indicates that the null hypothesis should be rejected when the test value is in the right, or is in the tail region. I'm sorry, I should say the tail region. And it's in the tail region on one side of the mean. Okay, so it's called a one-tailed test because if you're on one side of the mean, a specific side of the mean, and you're in the tail region, or in this case, the critical region. The critical region is located in the tail. Then we reject. Okay, a one-tailed test is either right-tailed or left-tailed, depending on the direction of the alternative hypothesis. So we'll show you how the rejection region looks like. Right now this is just vocab that we're going through, but we'll show you how it looks visually. To find the critical value, we're going to be using the procedure in confidence intervals. In a two-tailed test, the null hypothesis should be rejected when the test value is in either of the two tail regions. Okay? Three cases for alpha equals 0.01. So we're going to show you how to find the critical value if we have a significance level of 0.01. So we're going to be using the z-chart for this. All right. So we're going to need to pull the z-chart out. So I'm going to be using that for these cases. All right. So let's look at case 1 when we have a left-tailed test. So if we have a left-tailed test, then we're going to be using 0.01 to find our critical value, okay? So if we have a left-tailed test, use your significance level. That's all you have to do. So if you have significance level 1%, that's going to be the area you use to find your critical value. All right? Okay. So then we're going to go ahead and actually find. We're going to be showing you this critical value. So if we were to find it, right, then we would go to the z-chart, and we will look up 0.01 in the area here. Okay, so the closest thing to 0.01, we're going to need to, let me zoom out a little bit. Okay, the closest thing to 0.01 looks like this guy. This guy is the closest thing to 0.01. These are pretty. This one's pretty close as well, but this one's the closest. Okay, so that's 0.01 if you round it. So we got negative 2.33. So that's negative 2.33. There's a negative 2.3 right there. So that's the closest value. That will be our critical value in that case. So if we were to do that, then it would be negative 2.33. Okay? And so in this case, the value is negative. So the value will be negative since it is on the left side. Okay? At least, for the z. For case 2, the right-tailed test, what we do is instead of looking at the alpha on the left side, we're doing the right side. So that means we're doing 1 minus alpha. So in this case, it's 99%. So then we're going to be using 99%. And we're going to be looking up 99% here. All right? So in this case, if we look up 99%, that's pretty close to 99%. So it would be positive 2.33. Okay, so you can tell it's positive. So the value is going to be positive since it is on the right side. And if it's a two-tailed test, then you're going to look up what you're going to do. You're going to look up alpha divided by 2 and 1 minus alpha divided by 2, because now you're splitting the alpha into two tails. So since you're splitting the alpha into two tails, you're going to be dividing by 2 here. All right, so in this case, you're going to be doing 0.01 divided by 2, which is 0.005. That will help you with the left critical value. And then the 1 minus alpha divided by 2, which is 0.995, will help you with your right critical value. Okay, so if we were to look up the left critical value, so let me just say this is the left one. If we were to look up the left critical value in the z-chart, well, that's 0.005, which is between these two, right? So if I show you these, so it's you can choose one of these or do in between them, but let's just choose 0.0049, or let's choose 0.0051. So the first one here, so negative 2.57. Okay, so in that case, our critical value is around there, negative 2.5, negative 2.57. So approximately, I'm just going to say approximately negative 2.57. And if it's on the right side, then we look at 0.995 on the chart, but you'll see that we'll get the positive value here. So if you look at 0.995, oops, wrong table. 0.995. See, this is pretty close to 0.995, which is, 2.57. So see, we got the positive version. So z right so on the right side, we have z is approximately positive 2.57. Okay, so that's how we do it for a two-tailed test. So in the figure here, we're looking at, these are several cases that you can use. So if we were to have a left-tailed test, then this is how our bell curve will look like, and we have a cutoff right here. Okay, so this right here is my alpha. So if we have a left-tailed test, all of your alpha goes on the left side. Makes sense because it's a left-tailed test. And in our example, if you have a confidence level of 0.01, then your critical value is negative 2.33. Well, it makes sense because that's the number that we just got right here. That's the negative 2.33 that we got there. Okay, and if your confidence level is 0.05, then you're going to use negative 1.65. Okay, so this value will change. So this is your your z alpha is what you're looking for there. So that's your critical value. So yeah, we'll just label that critical value. So that's your critical value there. And this right here, this shaded region is your rejection region. Rejection or critical region. And this right here is your non-rejection region, aka your non-critical region. Okay, so non-rejection. So in this non-rejection region, we assume that H0 is true. Okay, in the non-rejection region. So if we're in the non-rejection region, we fail to reject H0. Okay, so in this case we assume H0 is true, and then that's the non-rejection. If we're in the rejection region, then we reject HO. All right. Okay, so if we're a right-tailed test, then our critical value goes on the right side, and the critical value is positive. If you're on the left side, the critical value is negative. In this case, this is my alpha, and now we know how to find the right side. So if you're doing the right-tailed test, you do 1 minus alpha. For the left-tailed test, you look up alpha. For the two-tailed test, you look up alpha divided by 2 and 1 minus alpha divided by 2. Okay, so that's how we got these two values. So you have two critical values, a negative critical value and a positive critical value. And this time your alpha is split between two tails, so this is why we divided by 2. Okay? Alright, so using table E in Appendix A, this is the table that I showed you, the Z table here. Find the critical value for the scenario and draw the appropriate figure showing the critical region. So we're going to quickly do the critical regions here. So since we're doing left-tailed test, we use alpha. So use 0.10. Okay, so we look this up. We get a Z. So we're going to look up 0.10 now. Okay, the closest thing to 0.10, it looks like that. So negative 1.28. So around there, negative 1.28. So negative 1.28. And if we look at our little cheat sheet here, they have negative 1.28, here. So if you see that, they have negative 1.28 there. So we could have used that as a cheat sheet, but I want to show you how to practice. And then the two-tailed test, for alpha equals 0.02, we're going to be doing alpha divided by 2, since we're doing a two-tailed test, and that's 0.01. Okay, we're going to have two critical values here, and I know that they're going to be plus or minus. So I don't even have to worry about the right side. I know that the right side is going to have the positive version of what I get on the left side. And this is like the trick to do this quickly. Just do the alpha divided by 2. And you can do the 1 minus alpha divided by 2, but we just figured out that you'll get the same value. So do it for 0.01. Let's see here. 0.01 was this guy. So it's negative 2.33. And we know it's going to be positive negative version, so we'll just do positive plus or minus 2.33 because it's a two-tailed test. So for the right-tailed test, we're going to be using 1 minus alpha, right? So we got to do 1 minus 0.005, which is 0.995. So we're going to be looking that up for our Z. So 0.995. Which is between those two, 0.995. So we'll say 2.57 for that, 2.57. So approximately 2.57, 2.58, and it's going to be positive because we're on the right side. So let's show you the picture for these guys. So A, we have a bell curve. All right. Here you have your mu, whatever the mu is, we're not sure, depends on the problem, right? So your mu is in the middle. We'll say that mu is equal to some value k, I don't know, whatever k is. And then we're doing the left-tailed test. So we're like over here. So then for this guy, and usually in the standard bell curve, the mu is 0. So we'll just use 0 here. In a standard bell curve, the mu is 0. So we should be using 0 here. So let me just change this to 0. If you're doing a standard bell curve with z-scores, you should be using 0. And then the standard deviation is going by 1s on each side. So negative 1.28 is somewhere around here. Okay, and then negative 2 is over here. All right, so then that's our left-tailed test, critical value. So then that's my alpha. So let me just erase this. So my alpha is 0.10 here. Okay. So for part B, we'll be doing the same thing here. In the middle, we have mu equal to 0, and we're going by 1s on each side. So 1, 2, 3, negative 1, negative 2, negative 3. And we have a two-tailed test. So we have negative 2.33, positive 2.33. and my alpha in each tail is 0.01. Okay, and then our last one, C, right-tailed test. Alpha is 0.005, so we got 2.57. And that's our alpha. And that rejection region alpha is 0.005. So notice that this is the non-rejection region. So that means we have if we reject, right? So if we're here, right, the rejection region, that's a rejection region there. So if we're there and we reject, then there's a 0.005% chance that we're wrong, okay? Because 99.5% of the time, we're gonna be okay. But if we're in the rejection region here, we just happen to be here and we reject, then there's a small chance that we're wrong. So that's what this rejection region is saying. It's like 0.5% because it's 0.005. Same thing for these guys. If I'm in any of these rejection regions, then and I reject, there's a small chance that I'm incorrect. There's a 1% or a 2% chance that I'm incorrect in my conclusion. All right, so let's discuss the process for hypothesis testing. So step 1, identify your hypotheses, identify the claim. We did that in the other problems earlier, stating the hypotheses. Step 2, find the critical values. Kind of showed you how to do that here, for Z anyways. Step 3, compute the test value. We haven't done that yet, so this will be in future lessons here. So we haven't done that yet. So future lessons, we'll talk about computing the test values. Right now we're just introducing the ideas, the concepts. Then make a decision to reject or fail to reject. Summarize. All right, so how do we summarize? How do we draw a conclusion? So if we reject the HO, the null hypothesis, and the claim is the null hypothesis, then we will say that there is enough evidence to reject the claim. That ... whatever the claim is. If the claim belongs to the alternative hypothesis, and we reject the null. So if we reject the null, that means that we're accepting the H1. Okay, so we can only reject or fail to reject HO, but we could accept H1. Okay, so H1 could be accepted or rejected, but HO is reject or fail to reject. Okay, so if we reject the null, and the claim is H1, then really we're supporting H1, right? So there is enough evidence to support the claim, and because the claim is H1. If we're failing to reject H0, then really we're rejecting the alternative, right? So we're saying, if we do not reject HO, right? Okay. So we do not reject HO, which means, and the claim is HO, so there is not enough evidence to reject HO. If we're not rejecting HO, but the claim is the alternative, then we say there is not enough evidence to support. So notice that if the claim is H1, we use the word support. So if the claim is H1, so claim H1, claim H1, and if we reject, then we say there is enough evidence. So reject HO, we say enough evidence. So rejecting HO means you have enough evidence to reject it, okay, or to support the claim or whatever. Okay, so we have enough evidence. And if we do not reject, right, then we say there is not enough evidence. Okay, so fail to reject. So this is fail to reject. So I'm just going to use FTR for fail to reject. So if we fail to reject, we use the words not enough evidence. Okay. And if the claim is H0, we use the word reject. So claim 8 is H0. Then we use the word reject. Okay. So those are some keywords. We'll be practicing these in the last few lessons. I just wanted you to have the table so that you have it, and we can refer to it when we do the summaries and the conclusions. Okay. All right. So these are the concepts, guys. There's a lot of concepts here. But we will be using these concepts throughout the unit. Okay, so we will be constantly referring to this process. Okay, and we'll be doing more practice as we go along. All right, guys, I hope this helps, and I will see you guys next time.